I'd just like to thank Georgie before for giving me the opportunity to speak today. It's really nice being in Brazil for the first time. Sorry? And the scientific committee, of course. Okay, so I'm a PhD student at École Polytechnique under the supervision of Stefano De Marco and Emmanuel Gobet that unfortunately are not here today. And this is joint work also with Alexandre Zou from Ponts-et-Chaussées. Okay, so before talking about multi-level Monte Carlo and initial margin, we're going to look at the general problem of nested expectation. So suppose you have two random variables, x and y. Okay, so here, they're independent, so that's important, and you have two functions, f and g, and you want to compute the following quantity. You want to compute the expectation of g of the expectation of some conditional expectation. So what you see here is that you have two expectations. You have one inner conditional expectation, the one here, and you have one outer expectation, the one here. So of course, since x and y are independent, you can rewrite the inner conditional expectation as this, introducing the notation EF of x. Okay, it's okay. Okay, so we're going to look at two estimators for this. So the nested one and the multi-level Monte Carlo one. And then we'll talk about a technique for getting lower and upper bounds for the estimation of the quantity I. Okay, so why would you want to look at the nested expectation problem? Well, because it arises in a lot of application in finance. So when you're looking at value at risk, you want to compute a probability that a loss function, which the loss function would, which is here a conditional expectation, will be superior to some threshold here. So if you look at a simple problem, so you give yourself a loss threshold L star. So actually what you're interested in is the following probability, and it actually fits the problem that I exposed in the first slide, where G would be the step function. As we'll see later, for initial margin computation, G is the absolute value. Okay, so I've just rewritten here the problem we're looking at. So actually what you see here is that it's just an expectation of some random variable. But remember, this term here is actually a conditional expectation. So when you look at this term here, the natural way of estimating this is just running a standard Monte Carlo. And this is, okay, so you're just considering M samples. So it'll be called the outer samples. But then again, you have no idea of the conditional expectation, of course. So you need to estimate this term, and you're going to run another standard Monte Carlo. And this time, you're going to use N inner samples. Okay, so let us just study this estimator. So suppose you have f and g sufficiently smooth functions. So the bias, of course, because of the inner conditional expectation, you have a bias for the estimator. And this bias is of order 1 over n. So that's important. And you can show that by a bias-variance decomposition, the MSE, the mean squared error, is upper bounded by the following here. So you see so you see here that if you want to achieve a mean squared error of order epsilon squared, just by taking so remember n is the inner samples and m is the outer samples. If you choose the following orders for the two samples, then you achieve the mean squared error that you wanted. Okay, but here the problem is that the cost is, of course, so the cost is only m times n, and the cost will be really high here. It'll be 1 over epsilon to the power of 3. So remember, for Monte Carlo simulation, the computational cost would just be 1 over epsilon squared. So you can ask yourself, can you do better? Okay, so we're gonna. So before I give you the MLMC or multi-level Monte Carlo estimator, I'm just going to talk about the idea of multi-level Monte Carlo that was actually introduced by, it was formalized by Giles in his seminal paper. So actually the idea is really simple. So suppose you have a random variable p, but you can only get approximation of this, okay? And suppose you have a sequence of approximation of p, so you have L plus 1 levels of approximation for the random variable p. P0 being the worst approximation that you have, but of course it costs less to simulate this. So actually what Giles writes, it's really simple idea, is that of course you could just estimate this quantity by running a standard Monte Carlo, but it's saying no, we're going to use the all the sequence approximating the random variable PL, and just by, okay, so here you see that the expectation of PL, so that's the quantity you're interested in, right? It's just equals to the expectation at the coarse level, like the worst level that you have, level 0, plus just the telescopic sum. So, so instead of estimating this quantity, you're going to estimate this and this. Okay, so of course, I must add that this, so the difference here will be actually really small. So in our problem, the PL is actually the estimation of the conditional expectation. So you see here is just, so you want to estimate the EF, which is here. Okay. Okay, so now time to look at the MLMC estimator. So consider two independent families of random variables. And now you don't, okay, so you don't have, you have a vector of levels, M and N. Remember, N needs to be increasing. And I'll just recall here the nested estimator that we had before. So really the multi-level estimation will be a sum of nested Monte Carlo estimators. So you're going to use, okay, so you're going to, remember, you want to estimate the, at first you want to estimate the expectation of P0 at the level 0. So what you're going to do is use a nested Monte Carlo with M0 outer samples and N0 inner samples. So that's the first estimate here. And then what you need, so remember you need two estimation. You need, so one for the expectation of P0 and one for the expectation of the difference. And that's, again, you're going to use nested Monte Carlo estimators to do so. But then choosing, okay, so here you need to take, okay, so here we're taking ML outer samples and choosing NL inner samples for this one. So that's PL, actually, we're approximating. And that's PL minus 1. So we're choosing NL minus 1. Okay. So you can actually conduct the same analysis that we did for the nested Monte Carlo estimator. So so remember, as I said, the multi-level Monte Carlo is just a sum of nested Monte Carlo. It's just a sum of L plus 1 nested Monte Carlo estimators. So actually what really counts is only the what happens at the finest level. So you kind of have the same thing that you did for the nested Monte Carlo, and you see that the bias is 1 over NL, which is the finest level. So now the computational cost is just the, okay, so it's again NL times ML as for the NMC estimator. But then you need, okay, so you have L plus 1 estimator, so you need to sum over all the NMC estimators that you have. Okay, so now you can look at the mean squared error, and you see what? You see that, so you still have the bias here, so you can't do, you cannot do anything about this, so it's over order 1 over NL squared. And then the variance is upper bounded by this quantity here. Okay, so so once again, assume that you want to achieve the mean squared error of order 1 epsilon squared. So you need, okay, so suppose you choose NL of this form, the inner samples. So remember, it's increasing. Then it gives you capital L, the number of levels that you have for the estimation. Then if you want to make this product independent of the level, you can, you can take this ML to be M0 2 to the power minus L. So you see that those two terms here and here cancel out, and you remain with a computational cost of this form. So what happens here is that choosing M0 of O of the following order, and L being fixed by the NL here, you get a computational cost of log epsilon squared and 1 over epsilon squared. So that's actually better than the nested Monte Carlo estimator. So we're really close to the best thing we can get. Remember, for the standard Monte Carlo, it's just 1 over epsilon squared. So what you can ask yourself now is, can you achieve the 1 over epsilon squared for the computational cost? And the answer is yes. So, okay, so what you can do, actually, so for the multi-level estimation, you can use all the simulations for variance reduction. So remember, so actually that's really, it's the same as before, but we didn't have the 1 over half here. So we just had this term. So now you, okay, so you still have this term, but then you're adding another, okay, you're using NL minus 1 plus 1 up to NL inner samples to reduce the variance. And you see that at each level, the variance gets improved, actually gets improved from NL to NL squared. And if you just conduct the same analysis as before, you get the wanted computational cost. Okay, so we're going to look now at just a lower and upper bounds for the quantity. Okay, so why would you want this? Well, because the problem with MLMC and NMC estimator is that you don't have confidence interval for this. It's not clear at all whether it would converge to some normally distributed random variable as the samples go to infinity. Okay, so suppose now that you have a G, which is the absolute value, that'll be important for us later on for initial margin. Then actually you can get quite easily a lower bound. It's just, so the following equality holds. It's just that for any phi here, for any function, so this equality holds, and you see that this expectation is non-nested. It's just well, normal expectation. So you can suppose that you have phi. You can just run a Monte Carlo simulation. So the proof is really easy. It's just one line, so you can do the same thing, kind of the same idea for the upper bound. So you have that for any random variable epsilon, such that the conditional expectation of epsilon given x is 0. You have the following, the quantity I is upper bounded by this, okay, and the equality holds for this, okay, that'll be important for simulations. Once again, it's just one line. Okay, so now coming to initial margins. So initial margin is deposits to cover potential mark-to-market losses during a period of liquidation, which is typically a 1 week. So the official reference about this is in the margin requirements for non-centrally cleared derivatives in 2015. And a lot of authors have actually talked about this. So Julien and Pierre, Henri Labordère have talked in their really nice book, Non-Linear Option Pricing, so they talk about it. But many of us, okay. So the model we're going to look at today is the following. So suppose you have just really simple model. You just have a single option with a payoff of I and maturity T in a Black-Scholes framework, okay? So just notation, the delta is defined as this. And in 2000, so really recent paper from actually Agarwal and my PhD supervisors. They showed that okay, so they showed that for a certain model for initial margin, they need to compute the following quantity. So we can talk about this later, but this comes actually from a correction of non-linear PDE that they use to get the initial margin. And you can artificially change this and rewrite the following as this by introducing some random variable u. So because of course it'll be hard to discretize this to compute the integral, you get a bias then. So what you do is just introduce the random variable u. Okay, so what you can do actually is rewrite the problem here. This problem in it fits the nested expectation that I presented on the first slide. So you just do some calculations, and you can rewrite this by defining this this function f, and g is the absolute value. Okay. See here that x is now okay. It's a 2D. It's a multivariable. Okay, so it's in R2, and y is just a normal distribution. Okay, so there's been actually, and there are many others there are a lot of people working on this at the moment. Okay, so Jai is in a revised version of his seminal paper actually worked on this. And he's proved that you can still achieve the computational cost 1/epsilon² if you suppose that G is smooth enough. Goldie, Juneja, Brody and al. Also achieve this by looking when G is a step function, but they require some really strong assumption on the conditional expectation and the estimation for the conditional expectation. And quite recently, Giles, again, and Ajali, okay, they look at the problem where G is a step function, and they look, and if you suppose that this random variable has a bounded density in the neighborhood of 0, they again achieve what we want. And what we did is actually really similar to this, though it is, I mean, it's a less strong assumption. Okay, so suppose that you have some function g of the following. So those two assumptions will usually be really, so they are easy to verify for the absolute value. And you need some small bull estimate for the conditional expectation here. So suppose this holds, then you can still achieve, so we've showed that you can still achieve the computational complexity of 1/epsilon² by choosing the following parameters for the MLMC estimators. So, okay, there are a lot of constants here, but just to make things clearer, if you suppose that P is infinity, so that happens in most cases in finance for the payoffs that we're looking at. So you see that okay, so that remains the same. It's just increasing samples, and ML will take the following form. Okay, so now we've looked actually at a simple case. So okay, you're not looking at call or puts, since remember we are looking at, so G is the absolute value. So you for call and puts, you know that the delta is either positive or negative. So actually. The absolute value will have no influence on this. So we're looking at a different payoff, a butterfly, and for the butterfly, okay, it doesn't, so it can be, it's first positive and then negative. So actually the small bull estimate assumption is actually quite hard to verify. It's really, it's some technical proof, but you can still show that the estimate holds. So the idea is that you need to, so what really matters actually is that when the delta is 0, you need to control the density of the butterfly's delta. And okay, so that's, so we did this, it's fair, okay, it's a technical proof, not going to go into too details, we can come up to that after. But some numerical now graphs. Okay, so we wanted to compare all estimators. Sorry. So if you look at this, so what you can do is okay, if you fix a cost and you run a grid search algorithm to find the parameters. Okay, so the problem with these methods is that so you get orders of something. So there are some constants. All the time you have M0 and 0L, so you need to estimate those. So by running a grid search algorithm, you can get so you get a good approximation of those. And if you look at these graphs, so what you see is that for fixed costs, you get the RMC here, so it's a log-log plot, and you see that the ML, the multi-level Monte Carlo antithetic, it's actually the ones that has the lowest RMC. And you see that after this, it's the ML, the multi-level standard, and then the nested Monte Carlo. That was just a graph to show that we still have the order, the first order for the RMC for this time epsilon. Okay. Okay. To finish, so as I said, so we need, of course, to get lower and upper bounds, because it means nothing if you're just estimating some number, but you don't know if it's, I mean, you don't know if it's a good estimate or not. So you get, as I said, you can get easily lower bound and upper bounds. So to do so, you need to estimate the conditional expectation. That's actually quite easy. You just look at some independent copy of x, y, and you're solving the following problems. And once you've done this, so once you've calibrated your estimators for the conditional expectation, you just reuse this. So of course you need a basis. I didn't say that, I should have, for the x. And you can do the kind of the same thing for the upper bound when you want to estimate the following quantity. And again, once you've calibrated this, you're using the approximation that you have. So we did this by choosing some bases for x and y, calibrating our estimators, and then running the the estimators. Okay, so here we can. Okay, so actually we have an idea of the butterfly since we know. Since we know the delta is actually in closed form, you can run a brute force Monte Carlo to get a fair approximation of the true value for the initial margin. And then you can, as I said, once you've calibrated this, you can get lower and upper bounds for the quantity I butterfly. So you see here that it increases, and then so it increases to this quantity, and then that's the upper bound, so it decreases. So of course, there's no reason why those goes to infinity. It would still decrease. Okay, so we did this for actually a lot of degrees. At that's actually the optimal value that we had. Okay.
Thank you very much. Do you have questions?
Thank you very much, Florian, for the very nice talk. Just, it's more a comment on like another application of this setting, which is, for instance, the calculation of VIX futures and VIX options.
Okay.
Typically in a model where you also have like what the volatility depends is not just pure stochastic volatility, but has a local volatility component. In which case, because the VIX at a later date is defined by a conditional expectation, and then VIX options are expectation today of a non-linear option of this conditional expectation. So that's exactly
a nested
the same kind of
expectation.
thing.
Okay.
Yeah. So
okay.
I mean,
it fits again in the.
Absolutely, it completely fits in your setting here. So that
okay.
I'm actually looking at this right now.
Yeah.
So we can discuss. Yeah.
And so have you? I mean, did you think about a way of? So are you running this again? I mean, are you just do a
doing for least squares Monte Carlos and like neural nets to estimate the inner conditional expectation, and then also as a result of this first step, like building upper and lower bounds in the lines of a paper by Guo and Loper that maybe you have seen.
Yes. So it's a bit different than.
Yeah, that's not the same technique. That.
Okay,
that
you can still. Okay. Yeah. Thank you.
So what are the confidence intervals that you showed on the final table?
Yes. Okay, so maybe I go here. So, okay, so once you've calibrated, let's say for the lower bound text, for example. So you have so now you have a phi once you've calibrated this, and you see here that okay, it's still an expectation. So you can get a confidence interval for this, and this you know that. I mean, if so, you take some samples to run. So it's just a standard Monte Carlo there, and And well, for this one, you know that taking independent random variables, you know that you'll have a confidence interval. So that's why.
Thank you.
I have a question as well.
Yes.
There are number of cases where of shapes of f where this calculation is obvious. I mean, if it's linear, if it's a product of x and a function of x and a function of y, and things like this, that opens an enormous door to control variate. Can you include control variate, you know, on top of this method?
Oh, you mean control variate plus antithetical?
Yeah, exactly. That is, I mean, well, essentially it means, okay, what if suppose that you have an f0 which is obvious to calculate, and then you try to find the f0 that is as close as possible to your f, and then...
Yes. Yeah, that's actually a good idea. Okay, we didn't think about this, but okay, could be something to look into. Okay, so you'd add, okay, you'll use this in there to...
You have a first guess for f, which is and sometimes, I mean, you can divide your error by a factor 100 by doing that.
Yeah, sure. Oh, we didn't think about this, so but okay, it's a good remark. Thanks.
Okay, so let's thank the speaker again, and then I think we'll have a little coffee break.